Imagine your ESP32 is part of a smart home network, and it needs to send temperature readings to a central server while also receiving commands from your mobile app. Understanding TCP and UDP is key here. TCP is like a phone call, reliable and sequential, ensuring every message is received in order, while UDP is like shouting across a room, fast, but you might miss a few words. In this lesson, we'll explore how to implement both protocols on ESP32, create client-server programs, monitor communication, and handle reliability or speed trade-offs. You'll gain hands-on skills that allow your devices to exchange data effectively in real-world IoT scenarios, preparing you to design robust networked systems immediately. TCP, or Transmission Control Protocol, is the backbone of reliable IoT communication. When your ESP32 connects to a server using TCP, it establishes a handshake, like a formal introduction, and ensures every byte of data is delivered in order. Think about sending a firmware update or financial data. Losing packets here can cause failures. TCP manages retransmission, sequencing, and connection state automatically, but it adds overhead and latency. In practice, you'll create TCP clients that send messages to a server and wait for acknowledgements. Consider how blocking calls can stall your ESP32. In larger systems, using non-blocking or event-driven TCP handlers prevents freezes and improves multitasking. Reflect on which of your IoT applications need this guaranteed reliability versus speed. UDP, or User Datagram Protocol, is the lightweight alternative to TCP. It sends data without establishing a formal connection, which makes it fast but unreliable. Picture your ESP32 sending real-time temperature or motion data to multiple devices simultaneously. Speed is more critical than guaranteed delivery. There is no acknowledgement, so packets can be lost or arrive out of order, but this is acceptable in telemetry or broadcast scenarios. Implementing UDP on ESP32 is straightforward. You create a UDP socket, specify the destination IP and port, and send packets. Keep in mind, UDP's simplicity comes at the cost of reliability. So for mission-critical commands or logging, combine it with high-level error checking. Let's implement a TCP client on ESP32 to connect to a server. The ESP32 connects to Wi-Fi, initiates a TCP connection to the server's IP and port, and sends a message. We use Wi-Fi client to manage the connection. Notice how we check client.connected before sending data. This prevents sending to a disconnected socket. Also, handling reconnection in the loop ensures your ESP32 recovers automatically if the network drops. Running this code, your serial monitor should print connected to server and any responses echoed by the server. Use a PC TCP server or Netcat for initial testing, and remember firewall settings can block connections unexpectedly. Now we'll explore UDP on ESP32. Unlike TCP, UDP doesn't require a handshake, so we can quickly send packets to a destination IP and port using Wi-Fi UDP. This makes it ideal for broadcasting sensor readings or real-time telemetry. On the serial monitor, each packet sent prints UDP packet sent. To verify delivery, you can run a UDP listener on a PC or another ESP32. Keep in mind that some packets might be lost due to network conditions, so you may need to implement high-level error checking in critical systems. Reflect, when would speed outweigh reliability in your IoT project? From years of deploying ESP32 networks, I've seen recurring issues. Blocking calls can freeze tasks. Always prefer non-blocking or event-driven approaches. Dynamic IPs can break client connections. Static IPs or MDNS help maintain reliability. Port conflicts are subtle but critical. Two services on the same port will fail silently. And finally, network reliability is unpredictable. Code your TCP clients to reconnect automatically and handle dropped UDP packets gracefully. Testing with simple tools like Netcat, Wireshark, or a second ESP32 makes debugging much faster. Think of networking as designing for uncertainty. You need robust strategies, not just working code. To reinforce learning, try building small projects. Set up 2 ESP32 boards for a TCP chat, sending messages back and forth. Implement a UDP broadcast system to stream sensor data to multiple devices simultaneously. For advanced practice, combine both protocols. Use TCP for critical commands and UDP for telemetry. Additionally, add Wi-Fi event handling to automatically reconnect on disconnects. These exercises teach real-world patterns, balancing speed, reliability, and multitasking in IoT networks. Reflect on your design choices. How would you prioritize protocol selection if devices move between networks or require low-latency updates? Hands-on experimentation here directly translates to practical skills for professional IoT projects. By completing this lesson, you've learned the fundamentals of TCP and UDP communication on ESP32, implemented client-server programs, and handled common network challenges. You now understand when to use TCP for reliability versus UDP for speed, how to test and debug both protocols, and how to design robust networked IoT systems. These are foundational skills that enable real-time data exchange, remote control, and scalable IoT deployments. Reflect on the trade-offs in your projects and experiment with hybrid solutions. These lessons form the backbone of any professional IoT engineer's networking toolkit.